So as we were trying to put together this conference and thinking about who we could bring in to help us promote the whole idea and inspire people toward craftsmanship, we came up with a short list of names of people that we think really embody what craftsmanship is all about. People who are eloquent speakers, people who are out there continuously promoting what we're trying to achieve, which is craftsmanship. Now, Micah Martin wasn't really available, so we got his dad to come out anyway. And so I'm very happy to announce Uncle Bob is here. If you haven't seen him speak before, I want to give you a little word of caution. He speaks kind of quietly, so you really have to be quiet and pay attention to what he's saying. And he really doesn't move around very much. He's kind of monotone and whatnot, but he has something really good to tell you guys. And I'm very, very happy to introduce Uncle Bob Martin.
I used to be a very dull guy, but that's all changed now. Okay, enough of that. So, who knows what the word laser stands for? Yeah.
Light amplification by stimulated emission of radiation.
Light amplification by stimulated emission of radiation. What the hell does that mean? We get the light idea, right? The light idea is not too hard to understand. You got to have multiple lasers, by the way. Anybody on stage, you got to have more than one laser. This is my green laser, and you can see that there's light that comes out of it, and that's fine. And radiation at the end, well, that's just light. So we've got light on one side, radiation on the other, but what's the stimulated emission part? And don't get crazy on me. Stimulated emission, and what is the amplification part? Who knows what a fermion is? A fermion is a particle of matter. Electrons, protons, neutrons, they are all fermions. And there's another kind of particle as well. It's called a boson. Bosons are things like photons and other interesting charge-carrying particles. A fermion has this interesting characteristic. It doesn't want to be in the same state as another fermion. So if you have two electrons in the same system, they must be in different states. One can spin right, one can spin left, but they cannot be in the same state together. If you put three electrons into the same system, one can spin right, one can spin left, and the other one's got to have a higher energy. This is why atoms are arranged in shells. They're all trying to follow this rule. This is called the Pauli exclusion principle. Nobody knows why this is true. It just is. Bosons follow the exact opposite rule. They love to be in the same state in the same system. They try to be in the same state in the same system. So imagine that we have a chunk of ruby in the shape of a cylinder, a ruby rod. Who saw The Fifth Element? Different ruby rod. We want a cylinder of ruby crystal. And what we're going to do is we are going to illuminate it with a 50 kilowatt light bulb. We're just going to blast away at it with light. Now it turns out that there are chromium atoms inside that ruby rod. And the chromium atoms have electrons, which are fermions. And when the photons of light hit those electrons, they bounce up into high energy states. But when they fall backwards, they emit a photon. And when they emit that photon, the photon can go in any random direction. And most of them just kind of head out of the crystal and don't do anything interesting. But every once in a while, one of those photons, by accident, will head down the length of the ruby rod And as it does so, it will pass by another chromium atom that is in a similarly activated state, and it will stimulate the emission of an identical photon. Now we have 2 photons, and these 2 photons are identical. They're going in the same direction. They have the same frequency. They are even in phase. And those 2 will pass by 2 more chromium atoms, and now you got 4. And then they tell 2 friends, and you've got 8, and they tell 2 friends, and you got 16, and then you get the amplification effect. Then you put a mirror at the end of the rod so that all those photons can move backwards. And then you put another mirror at the other side so that they can all bounce back and forth. And the one mirror, you silver 99.9%. 1/1000th of the photons can get out. And that's what you're seeing there. What's going on inside the laser is 1,000 times more intense than this. I got another laser. This is a talk about lasers, by the way. I got another laser here, which does not appear to be very interesting. It's this funny violet color. It kind of disappears if I shine it on things here. Not very bright. Oh, I wonder what this does. Somebody gave me a green band. Oh, look, it kind of turns blue. How weird is that? And then it's kind of violet there and over there. No, just not a very interesting. But I can kind of shine it on this. Watch what happens when the beam hits the lid. Woo! It was blue. It goes yellow. Holy crap. And it's bright. Look at how bright that is. It's not bright there. Right here. There's a lot of energy coming out of this thing. Well, we can't see most of it. I got a little pin here. The pin has got an orange plastic knob. Let's see if I can light up that knob. Ah! What kind of laser is this? $12, Amazon.com. It is an ultraviolet laser. This is an ultraviolet laser. They do not say that. The advertisement says that it is a blue-violet laser. That's BS. This is an ultraviolet laser. 90% of the energy coming out of this thing is in the near ultraviolet band. You can barely see the light energy coming out of it, the visible light. It's useless as a laser pointer, but it's a lot of fun to light up plastic stuff. And, you know, I've got these sunglasses that turn dark in the sun. I don't know if you can see that. There they are. You can use this laser to draw on your glasses. So, what we're going to talk about today is clean architecture. How many software developers do we have out in the room? Jesus, I can't see anybody. Yeah. Okay. Oh, we got lots of software people out in the room. Good. And have you ever had an architecture, a system architecture? If you have, might you have described it this way? Our architecture is a Java application. We use Eclipse to develop it. We're using Spring for lots of stuff and dependency injection and other junk like that. And they're using Tomcat as the web server and Hibernate on the front of the persistence engine and MySQL on the back for that. And of course, we're using Model View Controller. This is not an architecture. It's not even close to being an architecture. What you've got up there is a list of tools, not an architecture. It's as though I said, my house, the architecture of my house is a hammer and a saw and a tape measure. Spring and Hibernate and MySQL and all that stuff are not an architecture. They are a bunch of tools, and tools do not make your architecture. What does make your architecture? What should an architecture look like? Now, we can kind of see an architecture for that nice little gingerbread house there. You look at that gingerbread house and you can kind of tell, okay, that's It's a house. It's got one door. It's got a chimney, a nice kind of roof line. The architecture of that house tells you, I am a house. What other architectures could we look at? Wow. There's a library. If you look at that, you say, well, I can see some places where there's bookshelves. I can see bookshelves here. And, oh, gee, it looks like these are for magazines here. And, yeah, it looks like there's a desk here where there's some terminals. And you look over here, there's an entryway. Oh, that's a desk there that says circulation. Yeah, this is a library. You look at that for any length of time and you say, library. This is a library. The architecture tells you what it is. That one's a church. And it doesn't take very long to recognize it either. You look at that and go, cripe, that's a church. Look at that, there's an altar, a bunch of pews. This is where the kneeling rail is. People gather here, and they walk around in here, and then there's little offices where all the people go to talk about whatever they talk about at church. This architecture screams church. And that is an interesting definition of an architecture. A good architecture reveals the intent of the software that it represents. It reveals what the software does, what the software is used for. If it is an accounting application, the architecture should scream, I am an accounting application. But what do our architectures scream? I opened up an application not too long ago. It's a Rails app. How many people are doing Rails? They're all over in this corner. It's the Ruby area over there. Who's doing Java? Oh, a massive sea of hands. Who's doing .NET? Oh, interesting. Java people have it a little ahead of the .NET people. Who's doing Clojure? Well, one guy down the corner there is doing Clojure. Good, good. There'll be more of you later. This is a Rails application. In that Rails application, what you're seeing there is the top-level directory and all the folders inside that top-level directory. What do you think this application does? It certainly has controllers. It has models. It has views. So I guess there must be a UI. What else?
It's got tests.
Does. Well, specs. And it's got specs, which are tests, for the controllers and the models and the views, plus util and helpers. It's always nice to have util and helpers. Right? Util there. Oh, good. And helpers there, too. Good. So what does this application do? It's got some kind of a user interface. Looks like it's using model view controller as an internal organization scheme. But what are the use cases? And there's no way to see them. This architecture does not tell me what this application does. Now, you look at the top level of an application. What should you see? You should see all the use cases sitting there. You should see what the heck that software is doing. You open up the top level directory and you should say, oh my God, this is an accounting app. Or, oh my God, this is some kind of subway management system. You should be able to look at the top level and know what it is. If you could do that, imagine, right? Open up the top level and then there's all the use cases there. And then you say, oh, but I need to change one of those use cases. Which one? This one here because it's named. How do you have to change code now? You got to figure out what URL activates which particular controller, and then you've got to dig into that controller and figure out what the hell business objects it might talk to, and then you got to get into those business objects and see what the hell they're doing in there and what they're going to do to set up the views, because the views are going to reach into the business objects and pull kinds of crap out. And by the time you're done with that, 3 weeks are gone and you still don't know what the hell to do. This doesn't really help me. When you look at a software system and all you can see is model view controller in a web configuration, then the architecture of that system is hiding the use cases of that system and exposing the delivery mechanism, as though the delivery mechanism were somehow important. Now it's true, we have lived through the period of the web, what happened in 1998 and 99 and 2000, and the web just kind of took over everything we did. Who invented this damn thing? Al Gore, thank you. Yeah, no, it was the internet. Who invented this web thing? It's probably one of the worst ideas we've had in software. This awful markup language and this terrible request response thing where you've got to have these servers on the back end and they're generally stateless and you've got these browsers. And then what have we been doing with these browsers? Well, we've been putting code in those browsers. Lots of code in those browsers. Nowadays, we write whole applications to run inside the browsers. Why? Because we hate the damn web. This is what a web application looks like with model view controller. Got a bunch of controllers out here. They depend on the web. Got a bunch of business objects that have the appropriate abbreviation. Controllers depend on the business objects in a wide array. You pass some URL into a controller, some HTTP request, and the controller has to break it apart. Okay, what's this part here and this part there? Takes that whole URL apart. Maybe there's some form that came in, dig everything out of the form, try and get it all together. And then the controller has to say, okay, now I got all this data. I got to call that business object and this business object. I got to tell this one to do this one. That one's giving me this information. I got to give it to that one over there. The controller is orchestrating this dance. And then, when the controller is done orchestrating that dance, the controller says to the view, hey, view, do it. And the view wakes up and it goes, oh my God, and it starts to reach into the business objects and pulls out data here and it pulls out data there, and it mixes the data together and smashes it around, and then eventually formats it and puts it on the screen. Anybody seen a bunch of view files that reach into business objects? How awful is that? How terrible is that? Why should the views know about the business objects? Why should the views know which business object to go to? Why should the controllers know about the business object? Look at that rat's nest. How is anybody supposed to figure out what this system does? Anybody ever look through the paths thing? Go to the place where all the paths are, and this path goes to that controller, and this path goes to that controller, and this path goes to that controller, and you're trying to figure out what the hell the system does, and all you've really got is a list of URLs and controllers. And you still don't know what's in the views. That's what we're seeing here. Where are the use cases? Well, the use cases kind of start in here, and there's some use case code in here, but then it smears out over into these business objects. The use case code is kind of smeared around the business objects, and then oftentimes much of the use case code sits down in the views because the views gather it all up and fiddle with it and round it and do all interesting stuff, and they eventually put it out on the screen. There is no place for the use cases. The use cases don't exist in a single place. This isn't a failure. This is not good architecture. Now, the irony behind that is that we knew that this was bad architecture as early as 1993, 94. We had begun in those days to understand what architecture ought to be. There was a set of events that occurred during the middle 90s, before the web inserted itself into our lives, that allowed us to realize that the user interface should be separated from the use cases. that the UI should not know what the use cases are, that the use cases should not know what the UI is, that these two things were separate, and they ought to be kept separate. And we had made some progress along those lines, especially in the desktop arena, where we had begun to understand, oh, you can have a desktop app, and it can talk to these business things down here, and you can have a very nice separation, and then the web hit us. And the web was a sledgehammer. The web came along, and all of a sudden, everybody had to be doing web, and nobody knew how. And the year was 1999, and everybody was going, oh, cripe, we've got to be doing web this and web that, and we don't know what the hell web is, and maybe we can program it in C. No, that doesn't work. Well, maybe we can do it in C++. No, that doesn't work. What's this Java thing? Let's try that. Oh, that seems to work, sorta. Well, sorta. Not great. Oh, we've got this framework. These frameworks are starting to come. We've got frameworks like, what was the first web framework? EJB. EJB 1. Then there was EJB 2. Where did these things come from? They came from companies that were trying to facilitate their language. You understand why Java was written, don't you? You know why a language like Java exists? Gosling, who wrote it, was trying to come up with a language that he could put in a set-top box that controlled a cable television set-top box. But then Sun realized that if they controlled the language that programmers use, they controlled the programmers. It was a commercial activity, a very brilliant one, to gather the hearts and minds of programmers. This was not lost on Microsoft. They understood it particularly well. And at first they tried to do the same with Java, but then there was some legal difficulties with that, and they decided it would be better to change a few keywords into colons and claim they had a completely new language. And they invented C# in order to claim the hearts and minds of us. I want you to think about how bizarre it is that our mode of expression is owned by a company. And that company can do anything they want with that mode of expression. And by manipulating it, they manipulate us. Oh, you might think, well, their intentions are good, and I'm sure they are. But they're not well intended towards you. Now, Ruby's a different matter. Ruby came out of the hinterlands, invented by a lone guru off on the east somewhere, and he spread it around the world, and Andy and Dave took it and propagated it and made it a pleasant language. And Python is another language like that, a pleasant language. C was a language like that. C was not promoted by any company. AT&T didn't want to own it. They abandoned it as quickly as they could. They weren't trying to gather the hearts and minds of programmers. That was all Ritchie and Kernahan. Those were those guys who had made C. C++ was a language like that. AT&T didn't want that language. They gave it up as soon as they could. Strustrip was the dominator of that language until, of course, they turned it over to the Standards Committee. Do we have any C++ programmers here? Oh, God. Yeah, the things they've done with that language lately, I just shudder. I went to a Standards Committee meeting about a year and a half ago, and they were sitting there arguing over move constructors. What the hell is a move constructor? I didn't want to know. I left the meeting. A good architecture allows you to defer decisions about major chunks of the system. For example, the database. You don't want to decide on the database early. You'd like to be able to make your database decisions late. The data model. You don't want to decide on the data model early. You'd like to decide that late. What database tool are you going to use? Will it be Hibernate or something like that? Make that decision late. Which database vendor will you use? Will it be Oracle or MySQL? make that decision late. You might even make it towards something like Mongo. Does anybody know what Mongo is? You know what Mongo is as a database, or do you know what Mongo is? What? Document style database. No, Mongo. What's Mongo? It's the planet where Ming the Merciless ruled. Hey, Flash Gordon went there with Dale Arden. That's Mongo. Hey, call yourself geeks. Yikes. Delivery mechanisms. I want to defer them. I don't want to know that I'm using the web. I do not want to architect my system around the fact that it might be web delivered. I want to defer the whole web for as long as I possibly can. How many of you guys are writing Cucumber scripts? How many of you are doing web access in your Cucumber scripts? God damn it. Don't do that. You do use cases in your Cucumber scripts, but you do not have to talk through the web server. You do not have to pretend like you're actually doing a web application. You can defer that. You can defer things like Spring, the frameworks you're using. Got a bunch of guys out there doing Rails? Defer Rails for a while. You don't have to type Rails as the first thing you do in your project. You don't have to start with Rails. Start with the use cases. Start with some nice plain old Ruby objects. Get a few nice business rules going without a database, without the web, without any of that gunk. And then maybe you can start to decide, I wonder if this thing could be used with Rails. When the first thing you type is Rails, then Rails will dominate you forever. When the first thing you say to yourself is Spring and Hibernate and Tomcat, then they have you. And they will rule you. But if you start by saying, nope, just some use cases. I'm going to write a few use cases, not going to worry about frameworks, not going to worry about anything else, just use case here, use case there. I'm going to get some business rules going. After a while, you have enough information to make an informed decision about, what database should we use for this? What frameworks would help us here? When you have no code at all, you have no idea what those might be. Anyone who decides that Rails is simply pure good, Rails is Schindler's List, is deluding themselves. A good architecture maximizes the number of decisions not made. A good architecture allows you to push aside decisions, making them as irrelevant as possible for as long as possible. That is what a good architect does, and that is what the outcome of a good architecture. The role of the architect is to delay making decisions, to create structures that allow decisions to be deferred. Right now, we think that architecture is supposed to make all those decisions up front. What a great job. What a great job. I could get paid a lot of money to say Java, Eclipse, Spring, Tomcat, Hibernate, MVC. Thank you. What a great job. I want that job. And I never have to make anything work. I just walk away. Did you do it in MVC? Yes, but the project still doesn't work. Well, then your models and views weren't right. You did MVC wrong. You know what an architect is? A real architect? A real architect codes. A real architect spends time coding, spends time with the programmers in iterations, writing code so they know the hell that they've made for everybody. Right? That's what an architect does. That's how you get feedback on this hell that you've made for everybody. At this point, you might be thinking, well, Uncle Bob, you're nuts. Come on, you can't do an architecture without deciding these things. How the heck can you make an application without knowing what database you're going to use? So let me tell you the story. The year is 2001. I am just returning from OOPSLA, the object-oriented conference that used to be very popular. It's not anymore. And I had met Ward Cunningham there, and Ward Cunningham had shown me Fit. He had popped it open on his laptop. He had shown me this lovely tool that you could write tables in HTML, and those tables would turn red or green based on whether or not the application did what the tables said they should do. It was a testing tool, and it was lovely. And I said to Ward, Ward, how do you write your tables? And he says, well, I just kind of do them in Word and save them in HTML. I said, Ward, that's nuts. You should put a wiki around it. Ward is the inventor of wikis, by the way. And Ward said, yeah, well, maybe I should, but I've got other things to do. And I said, Ward, I'll put the wiki around it. And went home and started to write Fitness. Fitness is a wiki around fit. It's a wiki. Now, what does a wiki do? Well, a wiki stores pages. Okay, we're going to need a database for storing those pages. And that was our first thought. Our first thought was, okay, we're going to need a database around those pages. What database should it be? And since this is an open source project, it was kind of obvious we needed it to be MySQL. So we said, all right, we're going to get MySQL up. Let's spend a few days fiddling around with it. We'll come up with a schema. We'll fiddle around with MySQL. We'll get it working. And then one of us said, wait, we don't have to do that yet. Because one of the things that a wiki does is that it translates markup language to HTML. Yeah, it does, doesn't it? So we said, well, all right, that means that we could just write that wiki language parser and translator without ever investing in a database. Why don't we do that? And we spent 3 months getting all of the wiki language translated into HTML. But when we had all that working, and by the way, in order to do that, we created this thing called a wiki page. That was one of our objects, wiki page. And we derived from it something that we called mock wiki page. The wiki page class had store and load functions in it for a database. And the mock wiki page just didn't do anything with those functions. Eventually, we got all the translation code working. And then we said, all right, well, now we're going to have to actually get pages, and we're going to have to link pages to other pages and be able to read and write them, so we need a database. And somebody said, well, no, we don't, because what we could do is we could create a hash table in memory to store all the pages. And we could load that hash table with the load operator and store things in it with the store operator. It would pretend to be a database. And we said, yeah, that would be pretty simple. So we did that. And we derived a new class from wiki page called in-memory wiki page. And everybody just used the in-memory wiki page. And for a year, we wrote that wiki. And we wrote it, and we wrote it, and we got all the functions working. Eventually, we were using Fit with the wiki. We got everything done. We could demo it and all that stuff. Just couldn't save anything. Wasn't particularly useful. But all the functions were working. And then we said, well, now we need that database. And Michael Feathers was there at the time. And Michael Feathers said, well, no, you don't actually need it just yet, because it'd be pretty simple to take that hash table of pages and write it out to a bunch of flat files. We said, yeah, that would be simple, and it would allow us to make progress and test the system more. And still planning on putting it in MySQL, but all right, okay, we can do that. And he came back a day later with this file system page that he had derived from WikiPage, and we started using that. And with that, we had persistence. We were able to store tests and demonstrate tests and build projects. We could do everything. We'd take it on the road and show it to people. At some point, a few months later, we realized that we didn't need MySQL at all. That the file system was good enough. That it was fast enough, it did well enough. There was just no point in taking that last step. We had deferred the database project right off the end of the project. We had pushed it until it wasn't there. Oh, don't clap yet. Because as is usual with life, we had a customer. Nothing screws things up like a customer can. So this customer said to us, we got to have the pages in MySQL. what do you need the pages in MySQL for? It's a corporate policy. What? You have a corporate policy? Yes, all software assets must be in MySQL. What? Who writes these rules? Anyway, you can't fight City Hall. And so we said, well, look, since you have this problem, here's our wiki page class, here's our file system page class. Why don't you write a new derivative called MySQL page? He came back a day later with the whole thing in MySQL. We used to ship this as a plug-in to Fitness, but nobody used it, so we stopped. Now, there is a case where we took this fundamental decision, I must know the database, and we just pushed it right off the end of the world. And when somebody came back and finally demanded it, we could shim it in a day. That decision was not ever critical. And the architecture of the system, do you know that we have 2,000 unit tests in Fitness and 200 acceptance tests, and they all run in a minute and a half? Why do they run in a minute and a half? Because I'm not going to the disk. I'm not using the database except for a few tests. I never hit the database. I don't have to connect to the database. There is no database. I don't go to the flat file system. I keep it all in memory because we had all those in-memory page class and mock page class. We had all those classes already, so our tests go like lightning because we did not depend on the database early. Fascinating. Good by the way, who's got tests that are running slow? Shame on you. Your tests should not run slow. What happens when your tests run slow? You don't run them. That's right. They sit there happily saying, we are tests and we're so glad you wrote us. Would you please run us one day? And you say, no, because you're slow. And the tests say, can't you speed us up? We don't have time for you, silly tests. Thank your stars we don't just delete you. How many of you have deleted tests because they're too damn slow? Ah-ha-ha. It is a design imperative that your tests run quickly. There is no excuse for slow tests. I don't want to hear it. I don't want to hear the argument. I don't want to hear everybody saying, oh, but we've got so many. So the hell what? Do you know how fast these damn machines are running? Do you have any idea how many instructions this thing can execute per second? My laptop can do 10 billion instructions per second. Do you believe that to test your code, you need to execute more than 10 billion instructions? Does your code have 10 billion instructions in it? I think if your tests are running slowly, it's something else. Maybe you're depending on something that runs slowly, like a database or a web server. Maybe you're executing the same pathway over and over again. How many of you write tests that begin with login? Well, log in, then navigate, then we'll do the thing. Okay, now the next test. Log in, and then navigate, then we'll do the thing. Okay, now the next test. Log in, and then navigate. Are you idiots? If I have an accounting system, I expect the architecture of that accounting system to stand up and scream, I am a frickin' accounting system. I open up the top level of that hierarchy. I want to see use cases in there. I want to see things like add transaction, add to debit, add to credit, all the strange accounting things, whatever the hell they are. When looking at the architecture of a system, you should not be able to determine that it is a web-delivered system or a console-delivered system or a thick client-delivered system. The delivery mechanism should not be apparent because the delivery mechanism is a bolt-on. We should not see web-oriented models, views, and controllers at the top level. That doesn't mean they shouldn't be there. Model view controller is a very good pattern. We want to use it. I just don't want to see them at the top level. They're details. Those models, views, and controllers are details. What we should see at the top level are the use cases, because even the web is a detail. This guy's name is Ivar Jakobsen. Ivar Jakobsen's a friend of mine. He wrote a book in the early part of the 90s that became very popular around 1995. It's called Object-Oriented Software Engineering. Who's read this book? A few of you. Now the rest of you need to go get this book and read this book, because in this book he outlines the architecture that is based on use cases. This is the guy with his team, frankly, who solved this problem in the early 90s and presented to us a lovely solution. A solution that makes use cases independent, not just of the delivery, but of every other part of the system. Use cases don't depend on the database. Use cases don't depend on delivery. They are utterly independent little entities of business logic. They might look something like that. This is a use case for creating an order. And the use case tells you what kind of data comes in, does not tell you how it comes in, does not say that it comes in a form, does not say that it comes in through a thick client or a console interface. It just tells you what the data that comes in is. And then it says, okay, the order clerk is going to issue the create order command with the above data. That's a human activity. But the create order command is the important part. That's what starts this use case. The system will validate all the data. Oh, good. That means we're going to have to look at all this data and make sure it's okay. Haven't you already done that in JavaScript? I don't care. I'm not talking about JavaScript here. I'm just talking about the data coming in. The system creates order and determines the order ID. So somehow we're going to have to create the order. Isn't that a database operation? I don't care. Might be. I don't know. I'm just going to create the order somehow. And I'm going to get an order ID. Oh, you mean the key, right? No. I mean the order ID. I don't know what the heck a key is here. System delivers the order ID to the clerk. Oh, you mean he's going to put it up on a page? No. Somehow or another, he's just going to hand that ID back to the clerk. I don't know how. I don't want to know how. Imagine this as an incoming data structure. All that stuff there just packed into a nice little data structure. And you hand that data structure in to the use case object that controls create order. And what that use case object hands back to you is the order ID, whatever the hell that is, in another data structure. Thought of that way, a use case object is an object that takes in a data structure and emits another data structure. Can you test that? Can you test that quickly? Yeah, because there's nothing going on. Right? There's no disk, there's no UI, nothing's there. You can test that perfectly. Can you put all of your business rules into that form? Can you write objects that take in data structures, manipulate them according to business rules, output new data structures, and test every use case in your system without even thinking about a database? I'll leave you to answer that question. Use cases are not models, views, and controllers. They are not the controllers. They are not the models. A model view controller is a low-level structure, not a high-level structure. It's a low-level structure for controlling input and output. It is particularly aligned to user interfaces, except for the models, and even the models, because the models have these observer relationships on the views. According to Jakobsen, our architecture should be structured this way. This is not instead of model view controller. This is in addition to model view controller. We need entities. Entities are essentially business objects, the pure kind of business object that we're used to. And they are business objects that are application independent. Anybody got an enterprise? I hate to use the word, the E word. Anybody got an enterprise application? And a whole bunch of little applications inside it, but they all use the same business objects. An entity has application-independent business rules, which means that you can use the entities in many different applications because they have all the independent stuff. On the other hand, use cases, or what I call interactors in this case, have application-specific business rules. An interactor belongs to an application. An entity belongs to an enterprise. And the boundaries are interfaces. Java interfaces. In Ruby, you wouldn't use any code at all. You'd just have a polymorphic contract. Boundaries are interfaces that allow you to hand data structures across the user interface to interactor boundary. Your data structures come through the boundaries into the interactors talk to the entities, and then they hand data structures back through the boundaries to whatever is out there. When you think of it like that, the UI becomes an appendix hanging off the side of the application. The UI is not the central organizing principle. Anybody have an application where the web is the central organizing principle of the whole application? This is unfortunate. You would like your use cases to be the central organizing principle and the web to hang off the side as an appendix, which makes it easy to remove when it gets inflamed, because they do tend to get inflamed. Here's what this architecture might look like. I will have an interactor. This interactor will be for one use case. For every use case, I will have another interactor. I will have boundary interfaces. The boundary interfaces are used by the delivery to pass data into the interactor and for the interactor to pass data out. Their names are not boundary. Their names would be cleverer than that. Interactors would have the name of their use case in them, and the entities would actually be many. There would be many entities that the interactor would talk to in the typical case. There's my user. My user is sitting here. My user is talking to the delivery mechanism. I don't know what this delivery mechanism is. I don't care. The delivery mechanism will use a boundary interface which the interactor implements in order to receive the incoming data structure. The interactor will use another boundary interface which the delivery mechanism will implement in order to receive the result data structure. And the interactor will talk to many entities. When the user does whatever the user does, pushes a button or hits return or something, the delivery mechanism constructs a data structure called a request model. This data structure is pure data. There are no trappings of the web within it. There's nothing, you can't look at this data structure and know where it came from. It's just pure data. How does that get created? Well, if you looked in a web system, it would probably look something like this. You got an HTTP request that comes in from some browser somewhere. The web server catches it, runs it through the router, picks a controller, and the controller unpacks all the data and creates the request model data structure, and then hands it through the boundary to the interactor. You can see it move. It goes to the interactor. Now the interactor is looking at that data structure, trying to understand it. It knows that it's a create order. It knows the data within it. So it starts to use the entity objects. It starts to poke at them and prod them and say, well, we've got to create this order and we've got to put it here and we've got to do this. And the interactor controls the dance with the application independent entities. Then the interactor pulls the data out of the entities in order to construct a result model. That result model is a pure data structure. No trappings of the web. That gets transported back through the interactor, through the boundary to the delivery mechanism, where the delivery mechanism displays it to the user. Somehow. That interface right there, that's a test interface. It's also your UI interface, but it's your test interface. You can test the whole system right there. You can test every use case across that interface without the web being there. Anybody here have the problem that they can't run unit tests because the controller is always in the way? Excuse me, the container? You've always got the web server in the way, so you can't run unit tests? Why would you do that? Why would you bury your business rules behind this barrier that you cannot communicate through? That's an architecturally stupid thing to do. I don't have any container here. I can test the whole doggone thing right there. Oh, what about the database? Well, I'll show you that in a minute. How about the delivery mechanism? How do we actually get that stuff displayed? Now we get into web world a little bit. What's really implementing that boundary interface that the response model comes through is an object called a presenter. The presenter knows how to take this raw data structure and turn it into another data structure. I like data structures, by the way. Another data structure called the view model. Some of you .NET people know what this is. The view model is a webified result. We take all the stuff that's in the response model, we organize it, we turn it into strings, we round it, we put dollar signs in front and dots in it. We do all that stuff. We format the hell out of it. And then we finally hand it to the view. And I have drawn the view here so dim and diminished because there's no code in there. It's so damn stupid you don't even have to test it, because all the view does is say, get me the amount, put it there. Give me the date, put it there. Give me the name, put it there. That's it. It's not doing anything. Don't even write tests for it. If you organize your application that way, bunch of boundary interfaces right here, bunch of use case objects here, bunch of entity objects there, well, then you can have a web delivery if you like. They'll use the interfaces the way they want. You can have a console delivery mechanism. You can organize it the way they want. You could have a fitness fixture out here, and you could talk to your application. You could put anything out here. The delivery mechanism is an appendix hanging off the side. Look at the direction of the dependencies. Notice the direction that those dependencies move. They are all crossing the boundary pointing inwards. That's the definition of a plugin. The delivery has become a plugin. The web has become a plugin to the application. The application doesn't know it exists. The web is a plugin, which is exactly where it belongs. What about the database? How many of you recognize that picture? That's our system. The database is in the center, and it's big. It's important. It rules everything. There's a bunch of little stuff around the outside. It really doesn't matter because the database. Anybody made that interesting decision? Yeah, where should we put this function? I don't know where this function belongs. Put it in the database. The database becomes the dumping ground for every bad decision that you don't know how to make. I don't want to make this decision early. I want to get rid of this block. I want the database to be a plug-in to the application. I don't want the database in the middle. I want the database hanging off the side like an appendix, just like that delivery mechanism. And the technique for doing that is just the same. Typically, it'll be the interactors that need to talk to the database. We'll have them use some boundary interface, which here I have called an entity gateway. This is not a particularly imaginative name. You can do better. There will be some implementation below the line. That implementation is the thing that will talk to the database API. This might be Hibernate. This is where you might put Hibernate. I do not want Hibernate up here. This is your application. Keep the frameworks out of your application. You can put the framework down here if you want to. Put Hibernate there if you want. That's fine. Where does Active Record go, you Rails people? Goes down here. I don't want Active Record up here. Active Record is this big thing that screws everything up. Put it down here. Nice little implementation. You can have your interactors use that nice little interface to gather data, hand it to entities. You can control everything that way, which means that when you are testing, you can rip the database off and put something else in there, trivially. Some little thing that hands the right answers back for your particular tests. You can build mocks all you want all day long down here. You can mock out the gateways and all the different access methods. Where does the SQL go if you have a SQL database? It goes down here. I don't want any SQL up there. I don't want this to know about SQL. And that lets us test. Why do we test?
To emerge an API.
You said to emerge an API. Yes, we write tests to emerge an API. We use the API for our tests. But why do we test? How many of you are doing test-driven development? Oh, look at the number of hands in this room. That's probably like 30%. That's pretty good, right? Usually it's less than that. Then the number has been increasing steadily. 30% of you are doing test-driven development. Let me describe test-driven development to you, and then we'll see how many hands actually go up. Test-driven development has 3 laws. The first law, you are not allowed to write any production code at all until you have written a failing unit test. You must write the failing unit test first. Test-driven development does not mean write a bunch of code, then write a bunch of unit tests. That is not test-driven development. I don't know what that is. Some kind of crap. In test-driven development, you write the unit test first, then you make it pass. That's the first law. And already people look at that and think, well, that's just stupid. I mean, what sane person would write their tests first? What the heck would you test? There's no code to test. The second law is much worse. The second law says you are not allowed to write more of a unit test than is sufficient to fail. And not compiling is failing. So you write a line of a unit test, you're trying to call something on an object that you have not written yet. It will not compile. You must stop writing it. You must start writing a line of production code. But that line of production code will make the unit test compile. Which means the third law kicks in. You are not allowed to write more production code than is sufficient to pass the currently failing test. Now, if you do this, you'll be stuck in a loop. 30 seconds long, 20 seconds long. Just round and around this loop. Little test code, little production code, little test code, little production code. You'll never be able to write an algorithm. You'll never be able to write an if statement or a while loop. You'll always be interrupting yourself. The test code and the production code, the test code and the production code. What sane person would behave this way? But pick someone. Find a room of people who are doing this. Maybe at a code retreat. Pick one. Doesn't matter who you pick. Doesn't matter when you pick them. Sometime in the last minute or 2 or 3 or maybe 5, everything worked. Everything worked, everything executed, everything passed its tests. And it doesn't matter who you pick, and it doesn't matter when you pick them. Everything worked a couple of minutes ago. What would your life be like if everything always worked a couple of minutes ago? How much debugging do you think you would do? How many of you are good at the debugger? You know all the hotkeys, right? You know how to do a step into and a step over and a call out and a jump in. And you know how to set a breakpoint here and get to it 5 times and then set the breakpoint there and get to it 10 more times. And now the system is almost in the necessary state. We have to look at this variable, wait for it to be a 37. Now we can debug. This is not a skill to be desired. You don't want to be good at the debugger. If you're good at the debugger, it means you spend a lot of time debugging. I don't want you spending a lot of time debugging. And if your code worked a minute ago, you're not going to do a lot of debugging. Oh, we still debug every once in a while. It's still software. It's still hard. We still have these horrible bugs that take weeks to find, but not nearly as many of them. That would be one small advantage to those 3 laws. Another advantage. Imagine you've got a whole bunch of tests. Tests that test absolutely everything. And each one of those tests is 4 or 5 lines long. And every one of those 4 or 5 line long tests describes some part of the system. How many of you have integrated a third-party package? Okay, so you get this zip file from somebody, and you unpack the zip file, there's a PDF in there, and the PDF has got a manual in it written by some tech writer. At the back of the manual, there's an ugly section where the appendix is. All the code examples are there. Where's the first place you go? You go to the code examples. You don't want to read what the tech writer wrote. Right? You go to the code examples. You read the code, because the code will tell you the truth. These little unit tests that we're writing, 4 or 5 lines long, 6 lines long, 10 lines long, are little documents that describe how every part of the system works. You want to know how to create an object? There are tests that create that object every way it can be created. You want to know how to call an API? There are tests that call that API every way it can be called. And those tests are written in a language you know. They are utterly unambiguous. They are so formal they execute, and they cannot get out of sync with the system. They are the perfect kind of documentation. Just these dumb 3 laws gives us the perfect low-level documentation for a system. Code examples for the system. And if you don't like those 2, I've got another one, which is, how many of you have written tests after the fact? How much fun is this? It sucks, yeah. It's not fun at all. Why isn't it fun? Because you already know the code works. You've tested it manually. And now you have to write a bunch of stupid unit tests because some dildo over in the corner said you had to. Right? When you're writing tests first, that's a very different thing. But when you write tests after the fact, it's like, whatever. And then you find some part of the system where the test is hard to write. I don't know how I'm going to write this test. I gotta somehow test this function that's 12 levels deep, and it does weird things, and I don't know how I'm going to test it. And I tested it manually. I know it works. Screw the unit test. And you wind up with a test suite with holes in it. You wind up with a test suite that you know you cannot trust. If you write your tests first, why then you are composing the system in order to be testable. You must expose all the internals so you can test them. And a synonym for a testable system is a decoupled system. You have to decouple everything because you've got to test everything. So you wind up with a better design. But okay, fine. All of those benefits are meaningless. Here's the real benefit. How many of you have brought some code up? First of all, how many of you have been significantly slowed down by bad code? Okay, that one's universal. How many of you have brought that bad code up on your screen and said, I should clean this? And the next thought in your mind is, I'm not touching it. Because you know, if you touch it, you will break it. And if you break it, it becomes yours. So you walk away from the code. We are afraid of the code. We are afraid of it. It has dominated us. I want you to think of the incredible irresponsibility of being afraid of the thing you created, allowing it to have escaped from its cage and turn around and dominate you, so that now you react to it. It does not react to you. You stand in fear of it, wondering what it will do when you delete that semicolon. And you don't know. But what if you had a suite of tests that you trusted with your life? A suite of tests that you knew had no holes in it. A suite of tests that ran quickly, that when you ran it, and it said everything worked, was good enough to ship it. In fact, what if that were your QA process? What if your QA process was to run the tests, see them pass, ship it? Now, bring that code up on your screen, that dirty, ugly code. Oh, I should clean it. I'll clean a little bit. Run the tests. Oh, they still pass. I'll clean a little bit more. I'll run the test. Oh, they still pass. I'll clean a little bit more over here. I'll run the test. Oh, they still pass. You will clean the code without a thought. You will clean the code because you are not afraid of it. You will have mastered your fear of it. You will have put the code back in its cage. You will dominate it. It will not dominate you if you have that suite of tests. That is the real advantage to test-driven development. All that other stuff is crap by comparison. If you have a suite of tests that you trust with your life, you control the code. You can change it. You can clean it. You can take a terrible architecture and turn it into one that is nicely decoupled. I could go on like this for hours, but I think I should probably stop. Are there any questions? Sir?
Presentation available online?
Is the presentation available online? No. But I can make it so. Is there a site that we can put it on? Yes. Okay, fine. So we'll coordinate this. The presentation will be online. I will obscure it first, change the names and so on. No, I won't. Next.
Do you have an example of any of the applications built like this?
Do I have an example of any of the applications built like this? Many years ago, the year would have been 2002, I wrote a book called It was called Agile Software Development, Principles, Patterns, and Practices. Agile Software Development, Principles, Patterns, and Practices. In that book, there was a case study application, a payroll system. It was written in C++. It follows exactly this architecture. Several years after that, I co-authored a book with my son who could not be here today, so I came in his place. This book was called Agile Software Design Principles in C#. And the same case study was presented in C# with the same structure. Those two case studies are probably good enough to begin with. You can look at the structure of Fitness if you like. Fitness does this for the database particularly well, but we did not abstract out the web server because we were confused at the time. The web had addled our brains. And it took a while to understand, oh yes, we should have abstracted that. So you can look at Fitness for the database side, the website is not so clear. There are other applications out there. There will be more and more showing up. There's a whole bunch of guys doing projects right now to get them onto GitHub that demonstrate this as an architecture. So those are some places. Next.
So what would file structure for this set architecture, what would the file structure for this set architecture look like so that it would indicate to you that it was a library or a church?
Well, I'm not going to write software that's a library or a church, but what would the structure look like? I had for example, in the payroll application, I had a top-level directory I called them transactions. Now I would call them interactors. You might call them use cases. So right at the top level, use cases. And in there you would look and you would see all the different use cases properly named. Add employee, delete employee, change employee, pay employee, whatever. Add time card to employee. All of those little use cases would be in there appropriately named. So you'd have the use cases at the top level in a directory. You would very likely have the boundary objects at the top level if you were using a language like Java or C# where you actually have to have code for your interfaces. In the case of Ruby, you wouldn't need that unless you wanted to kind of document the interfaces with an abstract base class, but it's not really necessary in Ruby. And you might have a directory in there called the entities. And there would probably be quite a substructure to all of these. But you'd see those three up there at the top level. Anybody else?
Yeah, you said the key frameworks out of your application, and I think you meant things like Hibernate or Struts or some kind of a web framework. You don't mean to include a dependency injection framework,
So he says, I told him to keep frameworks out of his application, but did I also mean to include dependency injection in that? Yes. Dependency injection is an interesting one. We have gotten completely enamored by this technology. By the way, it's a really old technology, right? We've been injecting dependencies ever since there was software. But now we've got these interesting frameworks that can kind of do it for us. And we can create mammoth XML files that tell us every place we're going to inject everything. This is not a good strategy. There are things that need to be injected. Those things need to be injected into a plugin that the application doesn't know about. The application itself should not require any dependency injection because all of its dependencies are coming from its plugins around the outside. You'll have factories and strategies in plugins around the outside that are dependency injected. But then the application just uses them normally. So even the dependency injection would not reach all the way into the core architecture of the system. It would be used to instrument the outside plugins like the web or the database or whatever else was out there. And there was one more and then we'll quit. Sir.
The deferring of architectural decisions until as far as possible. Can you reconcile this with the ability to provide at least a little business value after like the second week and then a little more after the third week? And so how can you deploy an application without having made architectural decisions?
That is an excellent question. Okay. If we defer architectural decisions like the database and the web and all that stuff, then how can we follow the Agile principle that we should be delivering business value every iteration? And the answer to that is that you do not have to implement the real database or the real UI to show business value. You can implement phony ones, as we did in fitness, for example. We had in-memory page. We could demonstrate business value all day long. It's just that we couldn't store anything. Do you really need to have the thing web delivered to show that your business rules are being calculated properly? No. You could put a nice, simple little console interface on it if you wanted to. Or let's say that you did put a web interface on it. It would not have to be a fancy-dancy drag-and-drop AJAX interface yet. You could come up with some simple, stupid, horrible, forms-based thing that took you a half a day to wiggle together. As long as it was not coupled to the application, as long as it was a plug-in, you could demonstrate things working without all the glitter. Now, some people want the glitter first. Fine, write the glitter first. You don't have to write the business rules. But keep it decoupled. Don't allow the glitter to reach into the application and pollute the application with glitter. And with that, I think I will stop. Thank you very much for your attention.